In this video, we're going to discuss the type 2 error and power of a hypothesis test. If you recall from the beginning of this chapter, your type 2 error is basically the probability of not rejecting a false null hypothesis. We call it the beta. We have the Greek letter for beta, which kind of looks like a fancy capital B. And then the power of a hypothesis test, which is a new term, is the probability of not making a type 2 error. So your power is essentially equal to 1 minus your beta. Beta 2 is a probability. Your beta value is going to be between 0 and 1, and then so is power. Together, they will add up to 1. So this idea of not rejecting a false null hypothesis can be a little bit confusing. First of all, we have to think about the different types of means. When we run a hypothesis test, we start with mu sub 0. All of our hypothesis tests have this. This is that known factor, that value we believe to be true. And when we set up a hypothesis test, we always do something like, and I'm going to use that one with early onset dementia as an example. Remember when we set up H0, we said, oh, the mean is 55, meaning we felt the average age for early onset dementia was 55 because that was what's believed to be true. And then tests are done to determine if it is less than that. And in our problem, we would say, okay, perhaps it is less than 55. The 55 represents our mu sub 0. It is our null hypothesis mean, what we believe to be true. You know the Xbar comes from the sample. Okay, and we've worked with Xbar. It's just the average from your sample. But I'm going to introduce this another mean. Just because we believe that 55 to be true doesn't mean it's true. There's another mean that we're going to call the true mean. I'm going to designate it as mu sub A. Think of it as the actual mean. This is our true mean. If we were to actually take the average of every single member of the population, we can get a true mean. Often we do not know this. And if we knew the true mean, then we will be able to calculate our beta. So what we do is we kind of do a series of if-then statements. Well, if the true mean was really 54 instead of 55, then what is the probability of me making a type 2 error? What is the probability of not rejecting this null hypothesis? Because if the true mean is really 54, well, we should reject because this now is a false hypothesis if the true mean was really 54. But the problem is 54 is so close to the age of 55 that yes, even though it is smaller, the sample we would get from this would be so close that we probably would not get enough evidence, and therefore we would probably not reject. Hence, we have this large chance of making a type 2 error. And we would have a beta that's fairly big, say 80%, 90%. Now, let's look at the flip side of that. Let's suppose the true mean is really something as low as 48. So for some reason, scientists believe that the average age of early onset dementia is 55, but in reality, it's 48. Well, if in reality it's 48, and you take a sample from that population that has a mean of 48, there's a good chance that your X-bar is going to be much lower than 55. It's going to be closer to that 48 value, in which case our hypothesis test is most likely going to lead us to the conclusion of rejecting, and therefore giving us a very, very little chance of making a type 2 error. So the probability of making this type 2 error really does depend on your true mean. And we're going to see that because we're going to, as we go through this, we are going to work out what it is for the 54 and what it is for the 48. But before we get there, I kind of want to give you a little bit of an overview. I did a less than problem here. So let's think about this. We know, let's see, if our true mean if we believe it to be 55, and we are going to run a left-tailed test because we think it's less than 55. Okay, a left-tailed test, as we know, looks something like this. When we run this left-tailed test, where is our do not reject region? Our do not reject region is to the right, and this is our reject region. Now, since beta is the probability of not rejecting, ultimately, when we get to the second part of this test, this means our beta will end up being to the right. So we need to be careful because that's going to change. So for example, I'm just making this up, but let's suppose we did a two-tailed test. Well, now, where's your do not reject region? Your do not reject is in the middle. So when we go to calculate beta at the end of our problem, we are going to look at the area in between our critical values. Okay? And obviously, hopefully you get the idea now. If it's greater than, and we have a right-tailed test, well, where do you think the beta is going to be? When we ultimately go to calculate beta at the end of our problem, our beta then is going to be to the left, because that is our do not reject region. So this is something you need to think about before you go into the problem, because when we do get to those problems at the end, your normal curves are going to look very, very different. You have to understand which direction your beta, the area for your beta, is going to be in. Now, the other thing we need to keep in mind is, to do this test, we are going to add kind of another mean in here. We're going to find what we call a critical Xbar. The critical Xbar is calculated directly from our critical value. So when we do a critical value approach for a test, you know the critical value is that z-score that separates our rejection from our do not reject region. And in a left-tailed test, our z-score is negative. In a right-tailed test, and that z-score, of course, comes from our alpha, the z-score is positive. And then what happens in a two-tailed test? We end up with both a negative and a positive, but remember, you have to take that area and divide it in two. Our critical X-bars, the critical X-bar is basically the mean that gives you that exact critical value. In this case, we are going to use the negative z-score for the left-tailed test. For the two-tailed test, you would actually end up with two z-scores, which means you are going to have two critical X-bars. Now, the critical X-bar themselves is not going to be negative. Just the z-score to get them is going to be negative. And in a right-tailed test, you just end up with one critical X-bar. Okay? I think after we go through a problem, it will be helpful because we're going to do the left-tailed test. We are going to do this particular problem right here. I think it's going to be very helpful to watch the beginning of this video again, because then if you're doing a two-tailed test or a right-tailed test, it'll start to make a little bit more sense to you. So I'm going to go first, and I'm going to jot down the information for a problem. So again, I'm going to use a problem we've already worked on and did some hypothesis tests for. Now keep in mind, this is not a hypothesis test. There are going to be parts of it that are going to look a lot like a hypothesis test, but it is not. So this is the problem that represented the early onset dementia. So we have the mean equal 55. That's what we believe to be true. Then the alternative hypothesis, if you recall, we did this problem in an earlier video, was we believe it's less than 55. In this problem, we had a sigma, a population standard deviation of 6.8. We're going to work it at the alpha significance level of 0.01. Our sample size is 21. And what I want to do is I want to calculate two different betas. Now, when you do these problems in MATLAB or sample problems anywhere else, you might calculate 3 or 4 different betas depending on 3 or 4 different true means. But hopefully you'll get to see that once you do one of them, the subsequent ones become much easier. So the first thing we have to do, part 1, is to find the critical Xbar. So draw a picture. Always, always, always draw your pictures. Okay, this is a left-tailed test. So draw a picture of a left-tailed test. Get this idea in your head that where is the do not reject region in a left-tailed test? In fact, you might even want to say, you know, your do not reject region is in this direction, because that means your beta is going to be in this direction. Not right now, but when we get to the end of the problem, you'll see why I'm doing it now. Because your normal curve is going to look so different that you might accidentally go to the wrong side for the do not reject region. Now, to find your critical Xbar, you're going to use the formula you're very familiar with. But this time, we're going to use our critical value for our z-score. So instead of trying to find a z-score, a standardized score that matches our sample mean, and which ultimately becomes our test statistic, that z-score, we are going to figure out, okay, what would the sample mean be to get an exact z-score that is our critical value when our significance level is 0.01. All right, so this is where you go to your z-table, which I can pull up right here. Okay, we're going to go to that quick z-table to figure out what is the z-test statistic at 0.01. We're going to use 2.326. Now, again, this is why the pictures are so incredibly important. I want you to stop yourself. Negative or positive. Okay, clearly it's a left-tailed test. So that's going to be a negative 2.326. That's what we're going to plug in for the test statistic, for the Z standardized score. 2.326. Okay. We don't know Xbar. That's what we're looking for in this particular problem. We do know the mu sub 0 is 55. The sigma is 6.8 divided by square root of 21. Now, you will see different versions of this formula, of course, because if you rearrange the formula for Xbar, you'll get different versions of that. So you might see something like mu plus or minus or both, depending on left-tailed, right-tailed, of course, or two-tailed. z over sigma over square root of n. That is not a new formula. That is just this formula right here rearranged, but there really is no need to rearrange it. You can just plug it into the original formula. But you might see it in Math Lab or something along those lines. It is not a new formula. It's just this one rearranged. I just like to use the original. Okay, the next thing I would say is this number right here, this denominator, is going to come up in part 2 of this problem quite often. So you might want to just get that calculated. So take a moment, do 6.8 divided by square root of 21. I get 1.484. I would keep things rounded out 3 decimal places to get more accurate answers at the end. Okay? And just do your math really carefully. So now I've got negative 2.326 equals x bar minus 55 over 1.484. I'm going to multiply both sides by that 1.484. And when I multiply negative 2.326 by 1.484, I get negative 3.452. Equals x bar minus 55, and then of course add 55 to both sides. When I add 55 to that, I get 51.5. I'm going to go with 5 because it was 48. I'm good with 51.55. Okay, this is called the critical x bar value. The difference is if it were two-tailed, you're actually going to have 2 of these because you're going to have the positive and the minus. So you're going to take your 55 plus 3.452 and 55 minus 3.452. And then, of course, if it were right-tailed, your z-test statistic would be positive, so it would be 55 plus the 3 points. So they're the slight differences if we weren't doing a left-tailed test. But that part's done, all right? And the good news is part 1 is done for all the different true means. You do not need to redo part 1 for all these true means. All right, so now, part 2. We are actually going to now find beta, and we're going to pick one of the true means. I'm going to start with the one that is, further away. For true mean, mu sub a equal to 48. And if you recall at the beginning of the video, what did I say? If the true mean is that much smaller than the mean we believe to be true, and that true mean is where we're drawing our sample from, that sample is going to is very likely to provide sufficient evidence to reject. So the chances of us making a type 2 error are going to be really small if this were the true mean. So we should expect a really small beta here. If you kind of think through it ahead of time, you catch yourself if you're making any mistakes. All right, so how do we calculate that? Basically, what we're doing is just finding areas under a curve to calculate our true mean. Because again, if you draw a picture, okay, and we're going to now put that 48 center as the true mean, and our critical x bar of 51.5 is out here somewhere, okay? Well, the first thing I need to do is I need to standardize. So that means the 48, of course, goes to 0. And we need to get a standardized value of this mean of 51.5 if the true mean is 48. So we need a z-score. So again, we go back to this, but this time we're going to use our critical x bar for our x bar. So it's 51.55. And your mean, your population mean now is the 48. So notice the difference there. The sigma over square root of n stays the same, which is why I said we already calculated that. Remember, we said that was 1.484. So stop, go ahead, get your z-score, 51.55 minus 48 over 1.484. And mine comes out to 2.39. So this is a z-score 2.39. Now this is where I need you to stop. Beta, of course, is the probability of not rejecting. And this is where, at the beginning, when I had draw this picture, because remember, initially this was a left-tailed test. Which direction is the do not reject region in a left-tailed test? Okay, it's to the right. So when you come down here, notice this looks much different because this now looks like a right-tailed test, but it's not. It's still a left-tailed test. So our beta is in the same direction. Beta is going to be this area right here. And to find that beta, we need to go to our formula sheet and go to your Z table. Okay, let me go back to where I was. So the value, the Z value we want is 2.39. So 2.39 gives us, here's 2.3, right? So 2.39 gives us a value of 0.9916. But remember, this is the area in this direction is 0.9916. So this area here is 0.9916. How would we find beta? 1 minus 0.9916 should be 0.0084. So this side is 0.0084. So beta equals 0.0084, which we expected a small value, and that is definitely small. The power of this is a really powerful hypothesis test, because if this true mean really is that much smaller, you're going to have a very powerful test, is the 1 minus 0.0084, and that brings us back to 9916. So there's your beta, and there's your power. So the second part of part 2 is just doing the same thing for mu sub A equaling 54. Okay, we already have the critical X bar. That doesn't change. Okay, that's still 55.55. But now we're going to use for the mean minus 54. And I'm just going to go ahead and put that 1.484 in there. Now I get a value of negative 1.65. So I'm going to draw another picture. Okay, remember our 54 is now centered in the middle. Sorry, I just noticed I wrote 55 instead of 51. I apologize for that. That critical X bar was 51.55. I don't know why I put a 5 there. Yeah, so this is our critical X bar is here. And when we standardize it, I get negative 1.65. But I still want, still same type of problem. This direction is beta. Power's on the other side. Go to your Z table and look up negative 1.65. Negative 1.6. So negative 1.65. 0, 1, 2, 3, 4, 5. Looks to be about, make sure I got the right column. Yep. 0.0495. Keep in mind, This is the area to the left, 0.0495. To get beta, we have to do 1 minus. And that's going to be 0.9505. So beta equals 0.9505. We have a really high chance of making a type 2 error because our true mean is so close to the mean we believe to be true, our false mean, and then the power of this test is very low. Okay, keep in mind a couple things. Always draw your pictures. You're not always subtracting from 1 to get beta. If this were a right-tailed test, we wouldn't need to. We'd be given beta and have to subtract from 1 to get power. So you got to be really careful. Draw those pictures to help you figure out what's going on.